Hi, hello, good afternoon all. Welcome to today's joint webinar by our OEMs, Tasking and PLS. Today's topic is AURIX Multicore application development using tasking of compiler and PLS UDE debugger. We are from VVDN Technologies. VVDN Technologies is one-stop solution provider for embedded development tools, test and measuring equipments, which help us to set up and upgrade our complete lab establishments. It was founded in 2007, and we are delivering end-to-end embedded product engineering, cloud and ODM services. VVDN offers complete design services and manufacturing ecosystem, enabling customer product idea to reality. We are the authorized value-added reseller to sell and support tasking and PLS development tools in India. Please do visit our website for more info on upcoming webinars. That is www.vvdntools.com under events session. Do follow us in social media, LinkedIn, Facebook. Also subscribe our YouTube channel. And coming to today's agenda, how to improve performance using Tasking Tricore Toolset, linker script language tuning, introduction into Universal Debug Engine UDE from PLS, basic multicore debugging, outlook on trace-based debugging of timing problems, and tool demonstration. And finally, question and answers. If you have any doubts, any questions, you can use the chat box. We will address the same while Q&A session. And today's speakers, myself, Prasanna Kumar, working as a manager sales in VVDN Technologies, having 15 years of experience in industry in sales. I have worked with various embedded and automotive segment. I have handled multiple compilers and debugging tools. We have Mr. Mohamed Zuhair from Tasking. He is an electronics engineer having 12 plus years of industry experience in development and testing automotive electronics. He has worked in various functional safety compilers, supporting OEMs and Tier 1 customers in automotive semiconductors. Currently, he is working as a field application engineer for Tasking. His area of interest is on the multi-core with a focus on safety and security in automotive domain. We have one more speaker, Mr. Jens from PLS. He is a product marketing manager at PLS Development Tools. He joined the company in 2005 as a development engineer. He worked as a software architect and was actively involved in design of PLS innovative test and development tools. In the last years, he focused on tool support for on-chip emulators and trace. In 2016, he expanded his activities to the area of product management and technical marketing. Now, I would request Mr. Zuhair take it forward and continue the webinar.
Yeah, can you stop sharing? Okay. Good afternoon, everyone. So myself, Mohamed Zuhair, I am working as a FE for Tasking. So thank you, Prasanna. Thank you for the kind introduction. And thank you all for joining on today's webinar. So in this joint webinar between the Tasking and PLS, I am going to take care on the Tasking compiler part, and Jens from PLS, so he will explain you on the debugging part. I am sure that you might have saw in a lot of webinars our vision. So we think multi-core, creating the best possible performance on multi-core architecture for safety-related application is our focus. Before going to the topic of the webinar, I just want to give a glimpse on our various products in our product portfolio. As you know that, so we are not only into compiler, so we have a various huge list of products in our product portfolio. And our compiler has been developed with the ASPICE CL2 process. to qualify for safety critical application, and it's also a TUI certified compiler. And for the hardware configuration, we have a tasking pin mapper where you can quickly configure AURIX microcontrollers by making connections between port pins and peripherals. And if you're looking for some kind of an optimization tools, we have an embedded profiler and multi-core performance tool. So under this particular optimization tool, you can perform a lot of analysis where you can identify the CPU stalls, and you can able to see for your lines of code what is the maximum number of the CPU clock cycles. And even if you're working on a multi-core and if you want to do a balanced load between the cores, then you can make use of our multi-core performance tool. And even if you are working on any of the autos, and if you want to know the activity of your task under the autos, you can make use of these optimization tools. If you're working on any of the heavy math applications or an ADAS application, we have a LAPAC performance libraries, which is a linear algebra package performance libraries. And we do have a qualified libraries according to ISO 26262, which includes a safety manual and reports. And we have a standalone debugger also. And if you are working mostly on the safety critical sections, and if you want to ensure the freedom from interference between different ASIL levels with different components, we have a safety checker also. And we have a compiler qualification kit. So in this compiler qualification kit, so we'll be providing a safety manual, so which helps you to configure the tool chain for your safety critical applications. And we'll also providing some recommended use cases and mitigation strategies for the potential errors. And we have inspector tool. I'm sure that so you might have saw this in detail also in the previous thing. So where you can reduce manual code inspection significantly and provides guidance for the safety integrity level risk assessment. And last but not the least, now we are ready for next generation AURIX TC4X microcontroller also. So we have a smart code ID, and if you are already working and if you have a project already lined up for the next generation TC4X microcontroller, then feel free to contact us for any of the evaluation. If you need any of these evaluation for any of these tools, so you can get in touch with us. So as you know that the latest AURIX 3XX microcontrollers are well suited for safety related applications ranging from airbag, ADAS, braking, power steering, and other safety critical applications. And if you see the AURIX TC3XX family tricore processor memory architecture, it includes a lot of memories, including ECC protection. And you have a scratch pad memory, where each core provides a limited amount of PSPR and DSPR. And this memory usually we'll call that one as a near memory. And this type of memory can be addressed on each core without using the bus. So that's why they're extremely fast. And when compared to when you see about the flash memory as well as the RAM memory, so this type of memories are significantly larger when compared to a scratch pad memory, but is slower to access. Okay, so to take best advantage of tricore processor's flexible memory architecture, so the designer must be using a compiler that is aware of various types of memories. Okay, and you should select a compiler in such a way that so it should aware of various types of memories, and the linker should allow memory mapping configuration. So that's why the software architect or a designer should make use of the compiler which is having a complete knowledge on that. So in this particular webinar, so we had make use of a Infineon TC39X evaluation board, and the reference base example from the Infineon SMU emergency stop alarm for the TC39X family. So we took this particular example as a base example from Infineon, the safety management unit, which is a central hardware module which collects alarms from every hardware safety mechanism. So with this safety management unit, so you can able to configure your internal as well as the external reaction for each individual alarm. And by means of this SMU, you can able to monitoring of duration of internal error handlers also. So in that, so for this particular application, so we had make use of our TASKING Tricore Toolset and from the PLS UDE debugger. And the main purpose of this, so we want to show you so how you can improve the performance for your application by making use of tasking as well as the PLS. So I am sure that so you need to take a lot of aspects to consider if you want to improve the performance for your application. And if you see about the memory aspect, so you need to see and how you can move the data or a variable from so DAM, so default application memory to the so LMU, and from the LMU to the DSPR, and how you can make use of that. And apart from that, so some of the important aspects, so you need to take care. So while you work on tasking, so one of the important aspects for the in order to improve the performance is a tasking compiler optimization part, where I'm sure that you might have already used this particular option, where you can see the optimization level from so 0 to 3, where 0 is a none and 3 is a you can optimize the most. Where for the optimization level 0, it is going to be the same for the source code as well as the produce code. Whereas, and if you want to have a in detailed so information on the debug aspects point of view, then it is always recommended to have a O1. Okay, and with this optimization level, so you need to select between the trade-off between the speed and size, where you can see the level 0 is for the speed one and the level 4 is for the size one. And once if you select a T0, you'll get a high performance code with that of a T4 with the least code size. And we had compiled this particular application with lot of this combination, where you can see for the optimization 0 with the trade-off value, where you can see the performance as well as the code size. For this application, so I had selected various optimization level with the trade-off factor, where I can able to see some of the performance with the code size. So that's why in order to have a debug more in detail from the debugger perspective, it is always recommended to have a O1. In fact, you can also select a custom optimization also. You have an option to do that, where once if you select a custom optimization, so you have a chance to enable and disable whichever fits for your application. For example, if you want to so enable some unrolled small loops, and if you want to so enable the p-hole optimization, all these things you can select by means of a custom optimization. And apart from that, so floating point model is also one of the important things you need to take care of that in order to improve the performance. So tasking contains special variants of C libraries as well as the floating point libraries that uses a floating point unit instructions. So by default, the C compiler so assumes an FPU is present for the selected processor. So in order to get the maximum benefit of the floating point unit, so you need to treat double as a float. So you have that option if you are working on the Eclipse IDE. In fact, if you are working on some of the other mode also, so we have an option to do that. And if you see our floating point models, so you can see various models available. We have a model 0, model 1, and model 2, and model 3, where if you select a 2, you have a fast with a double precision. For a 3, you have a fast with a single precision, where you can see some of the things. It will omits all the checks in the fast single precision unit, and it will. And the third thing you can see, it will treats variable of type double as a float. And for this particular application, so I can able to see some of the things on the map file, which I can able to see on the debug folder of this particular application. And once if you select a fast double precision, what are the changes I can see in the map file, and what is the code size, and what if I select the third one, the fast and single precision, what is the code size, and how it reflects on the map file. So by this way, so you can able to select a multiple floating point model, so based on your application, so that you can improve the performance for your application. And also, so one of the important things is, so you need to how you are addressing. So how you are addressing your data, so by means of a far as well as for the absolute and near data. And if you make use of a so near data, it will select the first 16 KB in the each segment. And for this, if you see a small snippet of the code, so if you see the source code, then you can see how it has been addressed in various types of addressing mode. So once if you have a less pflash space, obviously it will be very, very fast. So that's why you need to make sure. So this is also one of the important aspects you need to consider. And if you're working and if you want to improve the performance for your application. And the next one of the important thing is, so we have a linker script language file. I'm sure that you might have saw on the Eclipse. So to make full use of the linker, you can script the information about the architecture of target processor and locating information. So the language for the script is called language script. So linker script language file. So it serves two purposes. So one is so you can enable in order to specify the characteristics of target board and of the course installed on the board. And by means of this LSL, so you can enables you to specify how sections should be located in memory. So by this way, you can change on your linker script language file in order to see how you can able to specify the sections on your memory. For example, if you want to assign some common code sections and if you want to group must start of the offset address from the beginning of p-fly0, then you can able to see all these reflections on the map file. And the same way, if you want to see if you want to assign some runtime library code sections to a group or a floating point library to a group or a standard library C library to a group, these things and all you can able to do by means of a linker script language file. And in fact, if you want to place those if you want to place those ROM copy sections to a dedicated memory range, so we have a different approach. So one solution is to make use of this keyword. Okay. And we also have so if you go to this, our resource section on our website, so we have a white paper also available where we showed a lot of tips and tricks for this LSL tuning. You can have a glance on this particular link also. So these things I'll show you on the linker script language file as well as how it reflects on the memory on the map file of the application also. And also we had done one of the case study for one of the MBench application. I'm sure that you might have heard about the MBench. MBench was explicitly designed to meet the requirement of modern connected embedded system. So before that, so people used to make use of a dry stone or a core mark in order to get the benchmarking result. Whereas nowadays, if you see, so MBench is one of the things where the requirement has been fulfilled for the modern connected embedded system. And we had done some of the changes on these particular aspects where we moved some of the things from DAM1 to LMU0, from LMU0 to DSPR0. And under the tasking perspective, we had changes on the optimization part, and we had done some of the changes and how we had selected some of the things on the floating point model and under the add MIL linking, all these things. So we could able to see the performance improvement. So by this way, so you can able to see a complete, we can able to improve the performance for your application. So next I will show you on the part how it is available. So I hope you can able to see my screen on the ID part.
Yes, visible.
Yeah, thank you. So this particular project I had imported. So once if you go to the file and if you see, so I had imported this particular project. So TMU Multicore Demo SMU Alarm. And if you right click on this particular properties, and if you go to the processor and you can see, so TC39XB, where I had connected an evaluation board of Infineon 39XB. And you can see we have a support for, and even if you want to see for the latest divide, and you can see our release notes on, we have released various patches. And if you go to the properties section again, and if you go for the settings part, and we have a lot of things. So for example, if you want to have a more in detail information on your console window, then you can able to select a verbose mode of control program. And under the optimization part, so that's what I want to show you, where you can see the optimization level with that of a trade-off factor. And the same way, for example, if you want to build for your application for wide optimization, then you can see you have a MIL linking also. And if you want to do a custom optimization directly, you can select from here. So from that, you can able to enable and disable whatever you want. So by this way, you can able to select the optimization perspective. And if you go for a floating point model, you can see you have a fast single precision, and you have, in fact, you have a custom also. If you want to treat double as a float, all these things you can able to select by means of a floating point model. And in fact, so if you want to comply your source code with that of a MISRA, so you can able to select that. For example, if you go for a custom, and if you want to comply your source code with that of a MISRA seed 2012 or 2004 or 1998, you can able to do that. And the same way, if you want to comply your source code for a cert C, you can do that also. And if you go to the linker part and under the script file, and which I want to show you, if I click on this particular file, then you can see, so some of the things I had modified. So for example, if you want to assign some common code section, and if you want to start at offset address from the beginning of flash file, so you need to define like this. And the same way, if you want to assign some standard libraries to a group, so you can able to tweak like this on the linker script language file. And the same way, so for various floating point library code or runtime libraries, and if you want to assign the ROM sections, so how you can define that, all these things. And if you want to know more in detail, so I request to refer that our tips and tricks on the LSL tuning section on our resource website section. So by this way, you can able to have a complete control on your linker script language file. So by this way, you can able to specify how section should be located on the memory part. And the same way, so if you want to generate output format, and if you want to, you can generate any of these output format. And if you want to generate a map file, then default you will have this option. And if you want to have a more in detail about the information about your application, then so you need to enable this particular option. And once if I start building my application, and you can able to see, so it is going to compile it, and it is going to generate. And so this one is why, because so it is I had enabled with the MISRA C 2012 enablement. So that's why you can able to see, since I had make use of, I want to compile my source code with that of a MISRA C 2012. And if I want to disable, so now if I want to compile my code again, so it is going to generate an ELF. So by this way, you can able to generate an ELF, then you can import that particular ELF file onto your PLS debugger. And the same way, once if you go to the debug section on the debug folder of your application, you can see the map file available. So this is the map file which has been generated. And if I open the map file here, you can see the map file which has been generated now. Okay, and if you go to the section, you can able to see the memory usage in bytes, about the code data, reserved memory, all this you can able to see. And the same way, you can able to see the complete layout of your what all the things you had selected. You can able to list out that. And the same way for the chip and for the groups, for the section, all these things you can able to see. Whatever the tweaks which I had done on my linker script language file, I can able to see, I can able to verify this on the map file. So what all the common constant data sections which I had allotted for the p/0, all these things I can able to see, and it is getting reflected on the map file. So by this way, you will have a complete information on that. So this is okay. So some points to remember. So in order to improve the things is, so you need to ensure that the program and data cache are enabled in the CStart files, and the tasking optimization settings can be used to trade off between the minimizing the code size and maximizing the code performance. Okay, so as I already recommended, in order to have a in detailed information on the debugging perspective, so we recommend to make use of the optimization 01. And in fact, so you can able to see, so you need to keep constant data in the near small memory. And if you want to tweak anything on the linker script language file in order to get the application up and running quickly, so you can modify that based on your application needs. And the floating point calculation, sometimes it will be a burdensome on system resources and application. So you need to make sure that you take advantage of the floating point hardware for optimal speed and precision. And also, so in order to see the complete detail in the confidence in the use of software tools, we have a compiler qualification kit. In this compiler qualification kit, so as I already mentioned, so we are providing a safety manual on part 8 chapter 11. So you can see, so we mentioned about the complete qualification program. We covers the complete software tool qualification process, and in fact we had demonstrated the capability of the tool set. So in this safety manual, so we have a evidence to support tool qualification method. So we had provided evidence of ISO compliance via C compiler validation test suite results. All these things we had provided. And in fact, we are also providing access to your tasking issues portal, where you'll have in detailed information on all the known tool issues. So the database includes a complete SIL qualification of issues and possible mitigations. So that's it from my side, from the tasking perspective. Now I will hand over to Jens.
So thank you, Mohamed, for taking the first part of this webinar. So I'd like to continue with the second part and give you an introduction into multi-core debugging with the PLS UDE debugger. We had now our application built by the tasking compiler, and now it's time to debug it in case it doesn't run as expected. And this is the topic for the next few minutes, and I'd like to show you how to debug it with the UDE. So my name is Jens Braunes. I'm working for PLS in Germany, and PLS is a company located in Germany that provides debug and trace and test tools for different kinds of microcontrollers, multi-core SoCs, especially in the embedded world, with support for controllers from Infineon, NXP, ST, Renesas, and so on. So before I begin with the demo, I'd like to say a few words about the UDE. So UDE is short and stands for Universal Debug Engine. It is a software development tool that provides extensive and powerful functions for debugging and system analysis of embedded systems or embedded software running on multi-core microcontrollers, multi-core SoCs, also single-core systems. The UDE consists of the actual debugger software running on a Windows PC and the access devices of our universal access device family. We call them UAD. So there are 3 of them. The smallest one, UAD2 Pro, for basic debugging purposes. The UAD2 Next, which is the all-round device, providing also trace support as well as Ethernet support to access the target in your company network, for example. And the high-end trace device is the UD3 Plus, which also can be accessed using a Ethernet interface, in addition to the standard USB interface that we have for all the devices. The debugger communicates to the target devices, the microcontrollers, via target-specific debug and trace interfaces of the supported multi-core SoCs and the microcontrollers, and the devices of our universal access device family guarantee a fast and reliable access to the target system by using optimized protocols and using all the functions that the target microcontrollers provide for debugging purposes. In addition to debugging on real hardware, which is the main focus for UDE, the debugger can also be used as a front end for virtual platforms or simulators, for example, for instruction set simulation for the Infineon Tricore architecture, especially the AURIX Tricore cores, or even for the Synopsys VDKs for different kinds of microcontroller architectures. This is especially useful for pre-silicon development. The latest case is for the new AURIX TC4X, the next generation of the AURIX microcontrollers. Here you can use UDE already for software and software development, test, and debugging. even if the silicon is not yet available to the product masses. Before we start debugging the application, we want to take a look at typical multi-core software architectures and the resulting consequences for debugging. The simplest software architecture is certainly a single core application. If you bring this into a multi-core system, then you can run several single core applications in parallel on the system. Each application comes with its own binary or ELF file and uses its own core. There are no or only minimal dependencies between them. And so debugging will in most cases focus on only one of these applications or one of the cores in such a system. So all the debug actions, especially run control, should be performed only on this specific core in focus. The opposite case is a monolithic multi-core application. The tasks and functions are distributed over all the available cores. We have a close dependencies between the cores, and we need synchronization of the debug actions. All cores must be stopped synchronously, for example. If the application hits, for example, a breakpoint, or you stop it manually, otherwise you will get an inconsistent state of the application immediately. And then we have, of course, a mix of both corner cases, different code bases and binaries for different cores. For example, for the main cores of the AURIX and for the GTM or the HSM, the hardware security module. And for this case, there might be a need to perform debug actions only on a subset of cores. So we need a partial debug synchronization possibility in the debugger. And all these cases can be handled using UDE. And in the next few minutes in the demo part, I'd like to show you how we can compile a monolithic application that we have already built with the tasking compiler. So the application is built into one single ELF file. That ELF file contains the binary, which should be loaded into the flash memory of our device. And the ELF file contains also all the debug information that the debugger needs to show the source code, for example, to know which are the variables and what functions exists and so on. So in our application, this Multicore Demo SMU alarm realizes a simple cooperative scheduler on core 1. That scheduler executes tasks based on fixed time slots. The timer for this is provided by core 0. And the correct timing behavior is observed. And if it's not met, then an alarm of the SMU, the safety management unit, is issued using a interrupt, and an alarm counter is incremented. That's a very basic example here how to use it. All the other cores are not doing very much except of executing some shared code. So shared code means that the code is based on the same source code. It is the same binary located at the same location into the flash, but it can be executed or is executed by any of the cores. The debugger hardware looks like that here, shown on the right side on this picture here. We have a target device with a TC39X mounted on an Infineon tri-board. The debugger hardware is the UID2 Pro from our Access device family. As said before, it is the base device of our family and connected via USB. You can see it here to my PC, where the UDE is running. And via a combined JTAG DAP adapter, it is connected. This is the adapter here to the DAP connector on the tri-board. This JTAG DAP adapter is the only target-specific part in the debugger setup. That means that the UID can also be used for other devices, for example, for devices from ARM, PowerPC-based devices, or devices from Renesas and so on. You only need to use another adapter to connect to different types of microcontrollers. And of course, you need the appropriate license. And then let's jump to the UDE. I hope you can see the UDE right now here. And the first thing I'd like to do is to create a debug session from scratch. So a debug session, we call it workspace, contains all the information that you need to debug a application. It contains of course, the ELF file, which application should be loaded to the target and to debug and should be debugged. Then it contains which target should be debugged, in our case the TC39, and also which connection should be used. And then all the windows you need, all the information you need for understanding your application. So let's start with creating a new workspace. At first, I give it a name, for example, test. And then you need to tell UDE which target you want to debug. So, and for this, we have a lot of predefined so-called target configurations here for all the supported microcontroller architectures and for almost all available evaluation boards. For example, we have for the TC39, the AURIX second generation microcontroller, a board from Infineon TC39B step, connecting using the DEP target interface. Then I finish that, save this target configuration file, and together with the workspace file, you can now start debugging. I select this file, and then UDE asked me which of the multi-core or which cores should be visible in the debugger and controlled by the debugger. In the default case, all the tricore-based main cores are selected. GDM is not selected here. I don't have any code for the GDM, and also the HSM is not available here because for the HSM, the hardware security module, you would need an addition package from us to allow debugging for the HSM. But all the features that I'd like to show you right now are also available for the HSM. Okay, then press OK, and then UDE connects to the target system. We see all the 6 cores are connected successfully, and you see right now that all the cores of this multi-core system are available in one user interface. So this is specific to UDE, so you have a system centric view to this to your multi-core system rather than a core centric view. And then I can load the application that we built with the tasking compiler, which is here located in the debug folder. I select the ELF file, and then I get this multi-core loader dialog opened, which allows us to select which core should be load the application into the flash. For the AURIX, it's always core 0, and for which cores we want to have debug information available in the debugger. In this case, all the cores. So blue checkbox means binary or hex load into the target. Green checkboxes means debug information should be available for the specific cores. I press OK, and then automatically the Flash tool gets opened, and I can program the application into the Flash. This is a warning that I get because the application changes the settings for the USBs in the compile in the target system, and so you have to be careful that you do it properly, because if you do it in wrong way, then you can break your target system. So I'm fine with that. So I've programmed the application into the Flash, and then I can start debugging. So, and from now on, you can open Windows, look into registers, to variables, and so on. I have already prepared a workspace for that. You can for sure save the workspace and use it the next day, and you can open a workspace on the next day. I have prepared one with some windows opened, and you see same application right now. The Flash 2 gets opened again, and to make sure this is the same application, then I can verify we have no differences here. Press exit, and then I can start the application. And you see here right now on top in the toolbar, you can see the status of all the cores. You can see each core has its own color. All the colors are used in the user interface of UDE for showing which window, which code, for example, which variables belongs to which core. You see also variables here colored. These colors indicates that the specific variables are located into the specific core local memories by the linker of the compiler, and all the Windows toolbars shows also the colors and indicates which are the core specific windows. And here we have some windows that are not core specific, indicating by this gray title bar here of the Windows. And you can see here all the cores are running right now. We have some variables that are changing during runtime. We have runtime watches here in UDE, of course. And now I'd like to show you how synchronized debugging is working. For that, let me browse for one of the task functions in core 1, for example, this one. And if I set a breakpoint here, then instantly it stops, of course, in this core 1. You can see it here. Also the status indicating in the toolbar by the core status control here, what we have on top. And you see also we are now stopping the application in core 0. And by looking at the toolbar here, you see that all the other cores are halted as well, synchronously with a very short delay after the core 1 was halted. And then I can, for example, do some single steppings, and you see also the other cores are doing some single steppings as well. So if I want to debug, for example, a application or some independent applications, or there is a need to debug only for one core and the other cores should not be stopped by debugging, then I can easily change the behavior of UDE for this synchronized debugging by using this Multicore Run Control Management. There are a group defined, all the cores that are part of this group are synchronized for debugging, and I can easily remove, for example, core 1. And if I then start the application on core 0, then all the other cores except of core 1 are started as well. You can see here the variables running, and core 1 is in halted state. I can do some single steppings here independently from the other cores, or I can do a go. You can see, okay, the breakpoint is hit again. Between the breakpoints, I see some changes here in this watch window. And this is a kind of partial debug synchronization. So if I want to put the core 1 back to the run control group, I have to stop the complete system because due to the hardware functionality of the AURIX, the run control groups can only be changed in halted state. And if I do that, then all the cores are now synchronized again. Okay, then I told you the other cores are doing some or executing some functions based on shared code. Due to the fact that all the breakpoints are core specific, it would be very annoying if you have a shared code to add a breakpoint on every instance of the shared code. So for that, we have defined, or we have developed a so-called multicore breakpoint. I switch now to another perspective in UDE. UDE allows to define several perspectives for different types of debug tasks. In this case, I'd like to focus on this shared C file on every core with this executed shared function. And if I set a breakpoint here, then you will see it is hit by core 0. And if I make it go again, then on every hold, I'm in core 0. And it seems the other cores are not executing this code, but that's not true. If I set instead a multi-core breakpoint, it looks a bit different, and you can see also for the other cores, the breakpoint is set automatically. And if you look at the breakpoint window, then we see here for all the cores, the breakpoint, the multi-core breakpoint is set. And if I start now the application, then you will see now we stop in the yellow core, which is the core 3. And if I start it again, then we are in the core 1 here right now. You can see also the active core on the toolbar, on the status bar, and so on. Okay, finally, I'd like to show you how to use trace for analyze the timing behavior of your system. At the very beginning, I told you that we have a alarm counter here, which is here, and which shows us it's counting up, and it shows us that sometimes the timing behavior or the timing constraints for the task scheduler is not met, and we want to analyze why. For that, I have also prepared another perspective with some trace-based analysis windows opened. And if I start the trace, I have configured it to trace the core 1 task scheduler here in a manner that we only trace the calls and returns of all the functions executed. That saves trace memory, which is limited on the target. And if the trace has been finished, then I can start the analysis of trace and have a first look into the execution sequence of all the tasks that are implemented and that are executed. And we see here that we have sometimes a long-running 50 millisecond task. This is takes too much time and prevents the task 10 millisecond to be executed. This is the first step you can do to analyze the timing behavior. The second step is you can create or analyze the core graph and do some profiling, which can be done with this core graph window here. And this provides us the core graph of our task scheduler, as well as some nice profiling information. And if we look at the maximum time for the 50 millisecond task, then you see it takes 14 millisecond in maximum, which is too long for this, honestly stupid implemented task scheduler. And from that, you can change your code and find a better implementation, for example. So time is over, and I'd like to end this debugger part and pass back to Prasanna from VVDN. Thank you.